Hey guys, wish you all a very good evening. How's it going? Guys, quick confirmation. Am I audible and is my screen visible? Perfect. Readable, yes. I'm not sure about audibility yet, but okay. I'm audible, right, guys? Can you just give a yes if I am audible? Actually, I was just taking another class right now. I had some audio issues, so I just wanted to make sure those are not carrying forward here. Okay, no audio issues? Perfect. Awesome. So as usual, let's wait for people to join in. Class will start in another 3 minutes. Cool. So if I remember last class, we were discussing named entity recognition, right? So we're going to complete that discussion today. If I remember correctly, we were only able to look at the architecture last class. So I will do a quick recap this class. I will spend some time discussing or revising those concepts which we saw last class. And then we will start talking about what attention is today. That's the broad agenda. As usual, let's wait for more people to join in. In the meantime, guys, any comments, concerns, feedback that you would like to share? Are you able to solve the assessments? Is everything going well? Is everything in life going well? Because that's the objective, right? To make our lives better. So I guess the first question should be, how is life for you guys? Hectic life. Yeah, I totally understand. Like, I mean, I took a trip with my family to actually take a break from it all, but like I'm still I end up working 80% of my time here. So yeah, hectic. I can relate to that. Amit says I missed the last two classes. How is this class related to previous one? Amit, today we're going to start talking about attention mechanisms, right? It is difficult to talk about attention unless you know what LSTMs are. So long short-term memory, right? The basic architecture of that, if you don't know that, you will find it a bit difficult to follow this class. My request to you would be to go back, at least watch the LSTM lecture before you come here. So yeah, last to last class was LSTM, right? It's very important actually. So yeah, sincere request is if you're not able to follow this class, right? It's a better idea to just drop off, watch that lecture and then come here. But oh, you have worked on LSTM? Okay, then great. Then great. If you know what I mean by recurrent connection, if you know what I mean by kernel, if you know all these terms, then we're good. If you worked on LSTM, you don't need to go back. Okay. And also, Amit, this class, I'm going to finish about 45 minutes of content from the previous class. Like there has been some spillover. So I think I will take about 45 minutes to discuss named entity recognition. So just try and follow along. Yeah. Just please try and follow along. If you have any specific questions and it's like a 1 minute question, then I'll try my best to answer. If not, you can ask your questions in the end of the class, right? I'll take them up at the end of the class. So yeah, we can do it that way. Cool. Okay, guys. So let's begin our class on attention. Okay. Of course, before we start talking about attention, we have to continue and complete our discussion from the last class. Broadly speaking, in the last class, we were dealing with this problem called named entity recognition. Can you guys quickly remind me what is named entity recognition? Like what is it? If I give you a sentence, what is it? What do I call a named entity recognition? Like what part of speech in that sentence will I call a named entity? Which part of speech will be associated with a named entity? Noun phrases. Perfect. So named entity recognition is all about making sense of noun phrases. Okay. That is what named entity recognition is. Last class, we had begun our discussion by talking about how we can apply different techniques to solve this problem. Okay. We had talked about some heuristic approaches where we are basically forming algorithms based on parts of speech tagging. So we will take a parts of speech tagger and then we will build some heuristics on top of that. That was the first technique that we had discussed. The next technique we had discussed is this probabilistic technique, which is known as conditional random fields, right? And the third technique, which we have been discussing for the past couple of classes, is that of LSTMs, right? So we take a we basically design a recurrent neural network which has a long short-term memory kind of architecture, right? Can you guys quickly tell me why is it known as long short-term memory? So let me break down this question. How many hidden states do I have in my LSTM? Two hidden states, right? The first hidden state is my short-term memory. The other one is a long-term memory. We basically take a lot of care in sending information from the short-term memory to the long-term memory in our architecture, right? Yeah. So that is the basic idea. Guys, in private chat, I have a question. Will I be covering NER using BERT in future lectures? Yes, we will be talking about BERT. I'm not entirely sure if I'll be talking about NER application of it, but we could discuss that once we've talked about BERT, right? It would be nice to talk about in what way you can use BERT to do NER. We can discuss that. Okay, cool. So this is essentially what we had discussed last class. We had talked, okay. So long short-term memory is what we have been learning. This is a architecture with two hidden states. We essentially create a bidirectional LSTM to solve the problem of named entity recognition. Any specific reason why bidirectional? Any specific reason? So for example, let us say I have the word New York, right? Is it okay for me to read the sentence up to the word new, or will I also need to know York before I can call it a named entity? What do you think? So my question to you is this. When I'm doing named entity recognition, do I need is knowing just the past okay, knowing just the future okay, or will I need both past and history? Both, right? Yes. Because I need both, it turns out that we have to use the bidirectional variant of LSTMs to do this task. Okay. That is essentially where we were, what we were discussing last class. Okay. Today, what we'll be discussing is how to combine these concepts of bidirectional LSTMs and CRFs to build an algorithm which is very, very robust. Okay. In fact, the state of the art in named entity recognition for biomedical applications right now is a bidirectional LSTM plus CRF. This technique is available, like a bidirectional LSTM plus CRF based NER method is available in this popular Python library called Stanza. Okay, so I will kind of run you through this library. They actually use this technique to get the best performance. It actually is as good as a BERT for this specific problem. So the performance of this bidirectional LSTM plus CRF is comparable to that of BERT. So this is one of the cases where this architecture actually achieves state of the art, which is why we're studying this. Okay. What we're going to be doing today is we are going to be coding this up for a different technique. Okay. We're not going to show you how Stanza did it from scratch. That would be a little too complicated and detailed to go through in the course of a 2-hour lecture. So what we're going to do is we're going to solve a toy problem using this bidirectional LSTM plus CRF. I'm going to show you how to code this up, and then you can sort of take a look at how the Stanza library trains their models to gain insights on how to actually apply this for this thing, right? How to apply this for main things. So Ajay, the problem with Stanza is they use a technique which requires a very, very large GPU system to do this training. And a lot of that cannot be discussed until I have access to that kind of a machine, right? So what we can do is we can sort of see how Stanza uses this technique to achieve state of the art, and we can leave it there. So as and when you get access to a machine like that, you can sort of carry out that training, right? The major roadblock here is the machine. Okay, cool. So yeah, then we're going to have a short introduction on attention mechanisms. I'm not very confident that I can complete this in one class. So what we're going to do is we're going to just discuss basic attention mechanisms today, and we'll cover the detailed code and everything next class, right? That is the basic plan for today. So let's get started. Cool. So let's quickly go through what all we had seen for the named entity recognition problem that we had seen last class, right? Okay. So the problem statement is as follows. We have been given this piece of text. What we have to do is we have to extract information from this. For example, you have symptoms being marked here, you have diseases being marked here, you have chemicals being marked here. So this is the kind of system that we need to build. Okay, that is our final objective. The question is why information extraction? Because more often than not, in an industrial application, you will have access to a lot of documentation, and to make sense of it, you'll have to build a system which can do this kind of extraction, right? So a named entity recognition system is very useful when it comes to information extraction, because it allows us to answer specific questions about from our document. So it's a good idea to build something like this. Broadly speaking, how do you solve this problem? You can solve this problem by applying either a pre-trained thing, pre-trained named entity recognizer. You can download a lot of useful ones from the internet. The Stanza library contains a lot of useful NER systems, or you can build something from scratch. And if a company is paying you to do deep learning, they'll probably expect you to build this from scratch. So what we're going to be discussing today is how to achieve this task, right? Okay. We saw some of the useful examples, like we saw some examples as to where this could be useful and all that. So we kind of went through those last class. Let's quickly revise what the classical approaches were, right? The classical approaches was this kind of a pipeline where you first apply something like parts of speech tagging, sentence segmentation, all that, and then you define your own rules for this, right? That is like a heuristic way of doing this. The machine learning way of doing this is to take documents with these annotations and apply any ML model to train it, and then annotate it for unseen documents using this ML trained model, right? Last class, I remember discussing what could be the possible shortcomings of this. It is all the shortcomings that normal machine learning algorithms have when it comes to text, right? What is that problem? In a word, contextual information, right? It becomes very difficult to capture contextual information in normal machine learning approaches. So what we have to do is we have to build a model which can actually capture the context somehow. That's our task. Okay, cool. So we saw various reasons why NER is difficult. And the first traditional approach that we had discussed last class is this linear CRF. Okay, quick recap over here, because this is going to be important later on. A linear CRF's job is basically to create this kind of a conditional probability field. What is the meaning of this? Okay, let us assume you have a sequence which is x1 to xn. Okay, so this is an n-length sequence. For each word in this sequence, you have to give a label over here, right? So if this is a word, what do you expect this label to tell me? In my NER problem, what can you give me some examples of what this label would be? So let us say I give you the word chloroform. What would be the output that you would give me? Noun, right? That is parts of speech tagging. But in named entity recognition, what do I expect from you? If we were doing parts of speech tagging, I totally agree. Noun is what we would have had. But if I give you chloroform, if I'm doing NER, I would expect you to tell me chemical and not noun. And that is the major difference between POS tagging and NER, right? NER is one level above parts of speech tagging. Okay, it's one level above that. So imagine now I have this set of words, I have this set of labels which are basically telling me whether or not this is a named entity, right? Named entity, whether this is a named entity or not. If I have something like this, then what CRF basically does is it defines a probability distribution where I have to find the probability of a certain label given the current word. Okay, given the current word, I have to find the label. And if you observe this equation carefully, the way I find this probability is I look at not just my current word, but my current label and my previous label. Okay, so think of it this way. Let us say you have already read a sentence up to XT. Okay, when I ask you to give me a label for XT, you are going to be making use of not only xt but also yt minus 1, right? That is what this function is telling us. This is a function of not only yi, which is my current label, it is also a function of my previous label. So broadly speaking, a linear CRF predicts labels by making use of information from the current word and the previous label. And the way it does this is it applies a softmax like expression these uh, on these functions. These are feature functions. Do you guys remember? We discussed this last class. Each fj over here is going to be a binary feature function. For example, this is going to be, is this a noun? Is this a verb? Those kinds of binary features which are local to this word. We're going to take many of those features. We're going to define such a feature function. We're going to pass it through a softmax. And then we're going to get this probability over here. Okay. So broadly speaking, what CRF takes as input is this sentence. It takes as input a labeled set of words, and then what it tries to predict is for a new unseen sentence, what is the predicted labels for that unseen sentence. The way it does this is it maximizes the probability of this sequence given this sequence. Okay, do we have a broad level understanding of how CRF works, guys? This is kind of important. I really want some honest feedback here. Do you understand what's happening in the CRF? Cool. Okay. 2 people understand in a class of 24. Okay. 5 people understand. 6 people understand. Okay, cool. So guys, we are now going to apply this concept. Okay. Just remember the input-output relationship. Input is a sentence. Output is the parts of speech. Named entity recognition tags. We are going to predict the current tag using the previous tag and the current word. Okay. This I want you to remember because this is what is going to be important in understanding how to apply to this bidirectional LSTM. Okay, cool. Okay, now let us quickly go through this. I had covered this architecture in detail last class. I want to quickly go through this and then we can move on to how to change this so that we can apply CRF also over here. Okay, let's do this. So of course, the input is a sentence. We saw paintings of Picasso. This is my input sentence. What am I going to do with the sentence? I'm first going to get the word embedding. How do I get word embeddings? Word2vec. Which word2vec algorithm is better out of the two that we have studied? Anyone remember? We had studied CBOW, continuous bag of words, and we had studied skipgrams. Which one do you remember being better? Skipgram, right? Okay. Why skipgram was better? Because it was like an essay writing task. It was like an essay writing task. It was not like a fill in the blank task. So skipgrams were better. So word embedding here is nothing but something like skipgram. Yes. Cool. So I have this word embedding over here. I take this word, convert it to its skipgram version of the vector, and I keep it over here. Then I also include some additional word features. This additional word features that I'm including here are usually the parts of speech tag, right? Like, is this a noun? Is this a pronoun? Is this a verb? Is this an adverb? That kind of information is now going to be encoded in this additional word feature over here. Then I'm going to have a CNN extracted character features here. Okay. Do you guys remember why this was important? Do you guys remember why this was important? Why should the next character matter? Why do I need a character level embedding? Something to do with English grammar, guys. Structure of the word, right? So for the same word, we can have different forms. Like we have better, like we have eat, eats, eaten. All these are basically different forms of the same word, right? So if we have some character level encoding of this word, right, we will be able to capture the structure of the word in that context, right? So that is the objective of including the CNN extracted char features. How do we do this? We essentially do character embeddings. We add additional character features like caps or all that. We apply a convolution layer and a dense layer over here. And the output of the final dense layer is what we call our CNN extracted character features. Okay. So a combination of all of these is what we feed into this bidirectional LSTM. Why is this a bidirectional LSTM? Because we have a forward thing over here, which is reading the sentence in the correct order. We saw paintings of Picasso, so it's going as is over here. But in the backward LSTM, the order is reversed. Here I'm feeding Picasso first, then I'm feeding off next, then I'm feeding paintings next. So the direction is reversed over here. Okay. Again, the reasoning for this is we want context information from present also, sorry, from the past also and the future also when we are doing this task, right? Okay. Finally, I have my output layer, which is going to give me a softmax tag scores, right? It's going to give me a softmax tag scores, and the final tag that I'm going to be doing is essentially based on this. Okay, cool. Is everyone convinced that this will work? Are we convinced that this will work? If we train this, we should get some accuracy, say 70%, let us say. Even if it's not 100%, let us say we reach 70% with this. Okay. Are you guys convinced that this will work? Give me a yes if you are, based on whatever you have seen of LSTMs, RNNs, all that. Okay, so we are fairly certain this will work, right? The question here is now, what is the problem with this and why should I combine this with CRF to improve results? Okay, that is the main thing now. What is the problem with this and why is CRF going to improve things for us? Let's focus on that point for a while. Now, do you guys notice that the output over here is depending purely on this LSTM cell and this LSTM cell, right? This output that you see here is purely depending on these two LSTM cells. Is this output over here taking into account the previous LSTM's output and the next LSTM's output directly? Is it really doing that? Not really, right? You can argue, see, I am doing a bidirectional LSTM. There is some encoding of this word over here, but this output that I'm getting here does not know anything about the actual prediction which was made over there, right? It doesn't know anything about the prediction that was made over there. So now the main intuition behind including a CRF over here is I want to make use of the prediction rather than just the encoded version. I want to make use of the predicted label for the previous word to give my prediction for this. Okay. This is the tiny problem with this bidirectional LSTM architecture, which CRF greatly improves upon. Okay. So when we see stanzas results, right, in the paper, we will see that this actually creates a huge effect. The major reason being, by default, there is no way for me to access the previous prediction to get this done. Okay, that's the reasoning over here. Cool. So let us now see how a bidirectional LSTM CRF looks like. This is what it looks like. I have my usual, so everything up to this point, right, guys? Okay, let me just do one thing. I'd rather take this and explain it on the notebook. Just one moment. Yeah. So now let's take a look at this structure. Okay. Yeah. So do you guys agree that everything up to this point, right? Everything up to this point is my bidirectional LSTM? Yes or no? The only additional thing over here is the CRF layer. Okay, cool. So now let's see what's happening to the CRF layer. The CRF layer is now going to take as input a concatenated version. Okay, why don't we have CNN here? It is captured over here. What is char representation, Indradeep? It's nothing but CNN extracted char features, right? It's CNN extracted char features. All I have done here is I have removed that CNN extracted word from here. It's still there. It's here. Yeah, it's still there. Okay, cool. So now let us see how we are designing the CRF layer. Let us see how we are designing the CRF layer. Before in CRF, right? Before in CRF, what we were giving this X1, X2, X3, Xn were the word embeddings. So we were figuring out these labels from word embeddings in the CRF only model. In the CRF plus LSTM, bidirectional LSTM, what we're doing is instead of giving the word embeddings directly, we are going to give the outputs of the forward LSTM and the backward LSTM to this. Okay. So think of it this way. If we were using just CRF, the only information we would have to predict the label would be the word embedding. Now we have a much better word embedding, which is taking into account contextual information, right? which is taking into account contextual information. So if I take the output of this forward LSTM, I take the output of this backward LSTM, I concatenate them in the form of a vector, and now use this vector to finally make the decision of which label to take, then overall, these two systems are solving each other's problems, right? The CRF gets a better word representation. The LSTM gets a better way to predict the next label using information from the previous label, right? So these two are kind of synergetic in that sense. Okay. So that is what we're doing here. We're essentially trying to build synergy by taking two systems which are solving each other's problems. So Azhar's question is, so this box will give embeddings? Yes, Azhar, right? Whatever LSTM output. So look at this. If I was using just bidirectional LSTM, right? If I was just using bidirectional LSTM, I would have to interpret this as a tag score. Now, instead of interpreting this as a tag score, I'm directly interpreting this as a possible tag score, and I'm using my CRF to make the final decision, right? So the embedding that you have over here is the output of the of both of these LSTMs, the forward and the backward. So you can think of this as a very good embedding, which also includes contextual information for my current word. This is one way to interpret this. Is that clear? Cool. Okay. So that is the main reasoning behind using both of these. Okay. That's the main reason behind using both of these. Now, let us actually train an NER from scratch. But like I said, guys, it's kind of difficult to show you how this is done for a very large corpus. What we are doing for the purposes of demonstration, what we have done is we have taken a smaller corpus. We're going to implement the code from scratch here. The same code can be used to train on the larger corpuses as well. The reason why we're not doing this is because very difficult to fit this on one GPU. In fact, if you look at Stanza, they talk about how they used 8 GPU systems to train their models. So the state of the art that you see from Stanza is the 8 GPU version. So kind of difficult to reproduce that. So let's make do with the best we can. Okay, cool. So let's see the code now. These are our usual inputs. I have hyperparameters. So guys, in general, if you want to test if a GPU is active or not, right, you can run this tf.test.is GPU available. This is kind of outdated. Okay, this is deprecated. Like I saw a warning here. So it's kind of better to use this function instead. So we have to basically check if this is null or not. So if I simply copy this over here and alternate, so let me just comment it here and let me put this here. So the alternate for this is if len of this list is exactly equal to 0, right? Is not equal to 0, then I will do the following. So this is how you get rid of this irritating warning over here. Okay. So this essentially gives you a list of the available GPUs. If that list is len 0, then we assume that there is no GPU. Okay. So what we've done here is if you have a GPU, we will use a batch size of 512. We'll use 5 epochs. We'll use max length as 75 and embedding length as 40. In the case of CPU training, we'll reduce the batch size and we'll reduce the embedding size. Okay. That is how we make everything fit and run in our lifetime, basically. Okay. That's what. So that's the reasoning here. Next, we're going to read our data set. Okay. So now I have this NER data set, which is not the same as the medical one. Okay. That is a point to note here. This is not a medical data set. Rather, it is a different data set, which is very commonly available. And most people test their methods using this. Okay. So this is known as the NER dataset. It's available on Kaggle and other sources, and it's used for benchmarking. Let's kind of see one example of this, right? So we have sentence 1 over here. Thousands of demonstrators have marched through London to protest the dash, right? If you notice here, the tag by default is O everywhere. The meaning of this O tag is this is not a named entity, right? That is how we interpret this O tag. Then whenever we have London, we have this tag here called BGO, right? I'll explain what this B means shortly. But for now, I want you to understand geo is basically geographical location. So the tags that we're kind of going to go through here, we're going to take a look at that shortly. First, let's talk about how to pre-process this data. Do you see all these nans over here? Not a number. We have to take care of these, no? See, here is the problem with this data set. It will give sentence one, and for the rest of the words uh, in that sentence, it is going to be a nan over here. So what we're going to do is we're going to fill these nans with the sentence number previously encountered, right? So we use this fill NA function with ffill, forward fill, right? Forward fill means I'm going to use sentence one to fill all the nans that I see here till I encounter the next one. So now once I apply this, I'm able to see that everything which is sentence one is marked as sentence one. So thousands of demonstrators have marched through London to protest the war in Iraq and demand the withdrawal of British troops from that country, full stop. Now this entire set of 24 words, right? This entire set of 24 words is my first sentence. So this is how we are pre-processing our data. Okay. Now let us sort of see what else is available in this data set. Along with the tag, this is the named entity recognition that we have to do. The other tag that we have available here is this part of speech tag. So the good thing is this data set already does it for us. We don't have to run this through Spacey again to get these parts of speech tags, right? It is already done for us and we can use these as it is. That is what we're going to do. Moving on, let us do some exploratory data analysis. We have a total of 47,959 sentences in this corpus. We have 35,178 unique words in this corpus. This is basically a dictionary size now. The number of unique labels that I have inside my tag column, which is my named entity recognition column, right? The number of unique labels that I have is 17. So let's quickly go through this. So I have IGO, iArt, iEve, BEve, BTIM, O, iOrg, IGP, all these, right? Let's quickly go through these now, what these mean. Geo is geographical entity, org is organization, per is person, GPE is geopolitical entity, TIM is time indicator, art is artifact, event is Eve, natural phenomenon is nat, okay? And then you have these I and B, right? I and B. So let's understand what these I and B parts mean, okay? So do you guys remember from our parts of speech tagging class, we had defined something which is known as a noun phrase. Do you guys remember this? Noun phrase word? Okay. So let me quickly recap this one. In case anyone doesn't remember, I'll quickly recap this, okay? Let us say I have this word here called cat, okay? Let us say I have a different word before this, fat. Let us say I have another word here before this called orange, right? And before this, let's say the rest of the sentence is called, what would you call an orange fat cat? How would you name an orange fat cat? What is the first word that comes to your mind? What would be the name for an orange fat cat? Garfield, right? Perfect. Okay. I'm not the only one. Okay. So let us say this is our sentence. Okay. What I want you to notice here is the first noun that we have encountered here is this, right? Noun. These two words before this noun are essentially adjectives associated with this noun. Do you guys see this? Do you guys see this? Okay. So my noun phrase is not just my noun, but all the adjectives along with this noun. Okay. This is how we are defining noun phrases. This is how we have defined noun phrases in our parts of speech class. This is how we're doing it today also. Okay. So now let's see the rules for this. So a noun phrase chunk is, okay, 1 minute. I think this is a bit difficult for you guys to read. I'll just zoom in. Okay. Is this better? Is this readable now? Okay. So a noun phrase chunk is defined by the expression DT question mark JJ star NN. Okay. This is how we define a noun phrase chunk. DT question mark represents 1 or 0 determiner words such as a, the, is. So actually this is also DT over here. In this sentence, this would be classified as DT. This is a determiner. It tells you how many, right? So the, his, hers, etc. All of these are DT. This is optional. JJ star represents one or more adjectives such as palatial, prosperous, plain, etc. Right? So this is essentially all the adjectives with this word. And finally, NN over here represents the noun. Okay. So what this I and B is basically telling us is, if I don't have this determiner and JJ, right? If I don't have these two things, then this is outside chunk. Okay. If these two are present, then this is a noun inside chunk. Okay, that is the difference here. If I have a label which starts with B org, right? Let us say it is a BGO. Let us look at BGO, right? Let us look at this BGO. Do you see that this London over here is a BGO? Why is this London here a BGO and not an IGO? This London here is a BGO because this does not have any determiners or adjectives before it. So it is an outside chunk noun. Whereas if there were, so in this sentence, right? In this sentence, I would call this cat as a I animal. Like, is there an animal thing here? No, there isn't. Okay, fine. Imagine there is a label which named entity recognizer for animals. So I would have this I animal over here. Okay, that's the main reason why this I and B are there. Cool. Everyone with me so far? Have we now understood what my tags look like and what they mean? Okay, cool. So in a class of 24, I'm teaching 5 people. Nice. I hope the others are also understanding, guys. I hope you're following along. Okay, cool. So let's move on. Let's continue with this. Let's continue with our implementation. I now have a distribution associated with all of these, right? I have a distribution associated with all of these. If I were to think of this as a classification problem, are my classes balanced over here? Are my classes balanced over here? No, right? This is a kind of a problem. We have to keep this problem in mind. Okay. We're going to do something special today to take care of this, to take care of the fact that there are hugely imbalanced data points here. For example, 88,000 words have no tags, 37,000 words have BGO, but only 51 words have INAT, right? Natural, NAT is what? Natural phenomenon. Okay. So we have a very, very huge imbalance over here. We have to do something special to take care of this. Just remember this. When we come to the solution, I'll point it out. Okay. So now let us, before we actually start discussing the technique itself, let us do our usual pre-processing pipeline, right? So let's kind of run through this really quick. For pre-processing, we will first put each sentence through a function which will put each of the words along with its position and tag together in a tuple. So we have to pre-process our data in a very specific way. We want to now form tuples where we have the word, the parts of speech tag, and the actual tag. All 3 of them need to come here. Okay. So this is the pre-processing that we're doing. And this is the line where it's happening. This ag function is a lambda function, which is going to take these 3 things and put it together in a tuple for us. Okay. This is what we have. This is a sentence getter is nothing but like an iterator which has this get next function. So we essentially just keep calling this to give us each of these. So let's take an example and understand this. This is what a sentence looks like. Like if I take, oh, sorry, I thought this was a sentence. No, if I take this first sentence, right? If I take this thousands of demonstrators have marched to blah, blah, blah. If I take this and I pass it through this sentence getter, I will get the following: thousands NNSO of in O demonstrators NNSO, so on, right? This is what we need to do to pre-process our data. Then let us quickly see what the distribution of our sentence length looks like. So len is the number of tokens over here. Tokens is basically a token now is a 3 tuple. Okay, it's a tuple of the word, the parts of speech tag, and the NER tag. Okay, if we now take the sentences and plot the distribution, it looks like a nice skewed distribution here, right? Skewed is expected because there is no maximum length on a sentence, but we do have a minimum length, right? So the skew is kind of expected, but it doesn't look too crazy. There seem to be some outliers which have 100 sentences. What we'll do is we'll simply get rid of them before we use these, because we don't want our model to get too big. right? So we will get rid of some of these long sentences, but even if we get rid of them, most of our sentences lie between 0 to 60. Okay, so this is how we will pre-process things. Okay, now the next steps we will do for pre-processing is we will convert each text word to an integer ID. What is this? Is this one-hot encoding? Isn't this like one-hot encoding? Each word is associated with a position in a vector. So this is what we'll do. We'll use this word to IDX dictionary. So we're essentially going to just use normal Python dictionaries to do all this. Okay, cool. And in order to feed our by LSTM CRF model, we need to ensure that text should be of the same length. You guys remember why, right? Last class, all our sentences have to be same length. Otherwise, there will be an unnecessary bias towards shorter sentences. Yes. To fix that, we will make sure all our sentences have the same length. How are we going to do this? We're going to use this pad sequences thing. And we're going to use this max len, which we have defined before, right? We defined max len to be 75, if you remember. That is what we're going to do here. So I basically now have an unknown word ke liye I have a position. I have a position for padding words, and everything else gets this dictionary representation, right? I'm using a set builder notation to build my dictionary here, right? Okay. Now let us pay attention to what all dictionaries we have. I have a word to IDX dictionary. If you give me a word, I will give you the index position in the one-hot encoded label. That is the job of this word to IDX dictionary. The IDX to word dictionary's job is to do the opposite of this, right? If I give you an IDX, you have to give me back the word. So this is nothing but the reverse of this. And then I have tag to IDX, right? So tag to IDX means I will basically take all the 17 tags that I have to do over here. I'm going to again assign some number to them. And the number I'm going to assign to them is this IDX. Okay. And of course, we're going to have some padding over here. So essentially, this is all we have. So 3 dictionaries to keep in mind: word to index, index to word, and tag to index. And of course, the opposite of tag to index, index to tag. Sorry. Of course, this is also required. I'll just add some space here so that I don't miss it out. Yeah, cool. Okay. So we have all these dictionaries. Then we will build our usual pre-processing pipeline where we convert each sentence from list of tokens to a list of word indices, right? Uh, then we will apply padding. Then we will convert tag label to tag index. We will pad each sentence to have the same length. We'll do one-hot encoding. And finally, we will have everything. So if we have to understand, if we have to summarize this entire cell, we have these, okay? So thousands of demonstrators, blah, 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 has raw label 0 BGO. This BGO is corresponding to London over here, right? Then this BGO is this Iraq. This BGPE is geopolitical entity, right? British troops. So British over here is the geopolitical entity. So that's what we have. After pre-processing, this looks like this. This is essentially the padded sequence of words, right? This sentence has only 24 words. The rest of the zeros are taking it all the way up till 60 or 75, one of those numbers. I'm not sure which one, but let's ignore that for now. It's one of the two. And the labels are, of course, going to look like this, right? Okay. Now comes the model building aspect of this by LSTM CRF, okay? So guys, what's nice is TensorFlow add-ons package already has implemented the CRF for us. There is this layer called CRF within this TensorFlow add-ons.layers. Okay, so we don't have to implement CRF from scratch. We can simply make use of this layer. It will internally do a lot of things for us. Okay, so there are some aspects of CRF which I have not covered in detail. One of those things is, if I give you the probabilities, how do you actually predict the entire sequence, right? That is done through something which is known as a Viterbi algorithm. It is a dynamic programming algorithm which searches through this huge matrix of probabilities and finds the best sequence. Quick question to the class. Have you ever encountered these shortest path algorithms? Shortest path algorithms. Have you heard of this before? Shortest path algorithms. Okay, cool. So just like shortest path algorithm has a greedy implementation. Okay. Some people have not. Okay, let me give you an idea. So in computer science, we have these optimization problems, right? Where we have to find the best sequence in within some constraints, okay? The intuitively speaking, if you try to solve that problem, you will end up with a program which will take a very long time, okay? Imagine you have to search within n factorial things for the best one. Isn't it an exponential algorithm? N factorial? N factorial has exponential growth, right? Yeah, it comes under NP-hard problems. It turns out that some problems, they may look like NP-hard problems, but they actually can be tackled using a very intelligent thing known as dynamic programming. The main logic behind dynamic programming is I will store the solutions to small problems. I will use these small problem solutions to build the large problem solution. Okay. So what I'm trying to tell you guys is what this CRF will give me is a huge matrix. I still have to look for the best sequence within this matrix. The Viterbi algorithm is a dynamic programming problem algorithm which solves this problem for you. Okay. If we were trying to implement the CRF from scratch, we would have to discuss how to implement that algorithm also. So we don't have to do that now. It is everything is done ready-made for us inside the CRF layer, and that is what I wanted to tell you about. Okay. We don't have to implement it from scratch, and this is good for us actually. Okay, cool. Now for the LSTM part, we are going to import the usual things from keras.layers. We're going to have LSTM embedding, dense, time distributed, dropout, bidirectional. We're going to use all of these today. Okay, to build our bidirectional LSTM. Okay. Also in this implementation, I believe we're not going to take into account the CNNs over here, right? I had mentioned CNN architecture, CNN character representations here. I don't believe we have implemented that. I'll check. Like I don't remember seeing that. Mostly that's not there. So let's confirm that, right? But otherwise, we have all the inputs required to build our model. Okay. Wait, I'll just go back there, right? Yeah. So this set of inputs has everything except for that char part, right? Okay. Now let's actually go ahead and build our bidirectional LSTM model. Okay. What we're going to do is we're going to keep the max length as 75. Our input dimension is this. This is nothing but the number of unique words, right? This is our vocabulary size. Embedding dimension by default is 200. If we have a CPU machine, this will go down, right? So these are just the default values for now. Okay. Model definition, of course, we have to start with an input. Then we have to define an embedding layer, which is going to take our word representation and convert it to an embedding. Then we have to define our output sequences. sklearn also has the CRF thing. Yes, Ajay. But the difference is this. In TensorFlow, CRF will be put into your computational graph, right? sklearn CRF won't come into your computational graph. So you won't be able to backpropagate over there if you use sklearn's one. What's nice about the CRF layer is whatever we learn, we'll be able to do backpropagation on it. So that's the advantage of using this one. So yeah. Okay. So now let's continue. We have this embedding. We have this variational by LSTM. So we have this output sequences, which is bidirectional of LSTM, where units is 50. Units 50 basically means I have the dimensionality of the output, right? The hidden state. So remember in LSTM, whatever the hidden state is, that is what we're giving as output. This units equal to 50 says fix the number of outputs as 50. That is what this is doing. Return sequences is true. We saw this last class. Why are we doing return sequences true? Because we want every single output associated with this LSTM here. Okay. So that is why we're doing this. We're going to apply this on our embeddings, and whatever this returns, we're going to stack it first. So again, we have a bidirectional LSTM with 50 units over here, which is stacking on top of this. Okay. Then we're going to apply a dense layer on the output. Okay. So what this LSTM will give to us at every time step is going to be a 50 length vector. we are going to apply a dense layer of 25. So this is a 25 cross 50 matrix if you think about it, because it will take a vector of length 50, give us a vector of length 25, and it will do it for every time step. Because we wanted to do this for every time step, we have to put this time distributed over here. Okay. So the job of this time distributed is to tell this dense layer, do it for every time step, not just one time step. Okay, cool. So on this output sequences, I'm basically going to apply this time distributed. Then comes the CRF layer. Okay. So the 18 over here basically tells you how many weights are going to be used in this, how many of those functions, right? So let's quickly go back to our CRF diagram. Do you guys see this FJ, right? This J over here is basically how many such feature maps am I going to take with these weights? So this 18 over there is controlling that for us. It's telling me how many such features should I build and use, okay? And what this model will end up learning through gradient descent is the weights. The WJs over there is what it's going to learn. So essentially, we're going to learn 18 weights because of the CRF model. Now, CRF, when you call the CRF on a dense output, right, it's going to give you a bunch of things. It's going to give you predicted sequence, potentials, sequence length, CRF kernel. Okay. Out of all of these, the only thing we are interested in is kind of this predicted sequence, right? So, yeah, no, my bad. What we're interested in is actually this potentials. Okay. So, the potentials is basically that huge matrix I was talking about. It's going to give you the conditional probability between every word and every tag pairing. So there is going to be a 17C3 35,814 C17 such pairings, and this is going to give us such a huge matrix for that. Okay, so we're going to use these potentials to finally get the predicted sequence. So now we're going to build our model which is going to take the input as this input as well as the potentials which is coming out of the CRF layer. Both of these are taken as input. We're going to compile this model using an Adam optimizer. And this is where I told you, remember I told you that we have to take care of this class imbalance problem. This is how we're taking care of it. Okay. Sigmoid focal cross entropy loss is a special type of cross entropy loss which handles the class imbalance problem. So if we did not observe a class imbalance, we would have kept this as cross entropy. But because we observed that, we will take the sigmoid focal cross entropy. If you guys are interested, there's a whole paper associated with this and why this makes more sense. I'll share the link. I think the links are present in this notebook. So you can check the last part of this notebook over here to see this. Okay. So this is how we build a bidirectional LSTM model with a CRF. We're going to do the usual things. We're going to have a save model checkpoint and a early stopping checkpoint. Okay. So we have all of this, and now we are ready to train this. Okay, cool. Before we go there, let's quickly see what potentials are. Potentials are outputs of the feature functions of CRF models. So basically that conditional probability. In a linear chain CRF, they're further divided into transition and emission potentials. So let me just explain this really quick. A transition potential is the conditional probability of encountering yi plus 1 given yi and x. That is the transition. So basically it's the potential associated with the transition, change of state. Okay. The emission potential is the potential due to being in this state. So the conditional probability of being in this state is the emission potential. The conditional probability of transitioning from yi minus 1 to yi is the transition potential. Okay. If you're interested in the math of this, right, guys, I'll show you one place. If you click that link over here, right? If you click this link over here, you can actually come down a little bit. Okay, this guy it goes through it very quickly. There is another link over here. This link is really, really good for understanding CRF math in detail. Okay, so if you guys are interested in exploring this in depth, I would suggest you read this. This is very simply put, guys. If you have followed through our linear algebra classes in Scalar, you will be able to follow this. Okay, so I guarantee that if you read this, you'll be able to understand. It's just a little bit out of scope right now. Let's just treat this as a black box layer and use this. Okay, cool. So now all we are going to do is we're going to apply this model.fit function. Okay. Once we apply this, it's essentially going to train. So this trained for a long time, and what's visible here is just the last one. It took 76 seconds per epoch, right? Okay. So once we do this, so the objective up to this point was just to show you how to build this model and how to train it, right? We're not actually going to go into this one. We're not actually going to go into the details of this. Okay. So this is where we stop. We're not going to explore how well we did and all that, because we know that this is not the problem we wanted to solve. The major problem that we wanted to solve was for this drugs case, right? Why are we not able to solve this? Because we don't have a good enough data set. The data sets which Stanza uses are GBs in size. And of course, it's not going to be possible for us to learn that. So that is why what we're going to do is we're quickly going to run you through this Stanza thing. Okay. So from this point on in this notebook, it's just an explanation of how Stanza works. Okay, guys. So don't get confused if this has got nothing to do with the problem we started with. I know that's confusing a little bit, but from this point on, we're just going to be discussing how to use Stanza to solve this problem. So we have this data set, which is drugs comtrain raw.csv. We have different drug names, different conditions, and different reviews. What we are going to do now is we're going to explore how to use Stanza to do named entity recognition on this review set. Okay, we're simply going to apply Stanza on this named entity recognition. And what we're going to do is for everything we detect here, we're going to interpret it as a side effect of this drug. Okay, so Stanza by default gives us a named entity recognizer, which is able to identify diseases and chemicals and stuff like that, right? Of course, if there's a review, most likely it will only contain diseases. So what we're going to do now is we're going to take Stanza, we're going to apply it on these reviews. We're going to see all the diseases that are detected over here, and we're going to call those diseases the side effects of this. Okay. So that is what the rest of this notebook does. I'm going to run through this really quick. Okay. First of all, we're going to gain a small understanding for what the reviews here look like, right? So if I run a word cloud on this, okay, the biggest word, the biggest word is not a number, which is kind of funny to me because it means that pre-processing did not happen properly. But apart from that, we have take, side, oral, fourth, halfway, effect, combination, weak, all that, right? So broadly speaking, we do get some words over here which talk about side effects. So we have to now take these review columns and detect diseases that are discussed in this review. Okay. So for this, we're going to use something which is known as biomedical NER Stanza. So Stanza is a library which has many domain specific named entity recognizers. Okay. What we are going to be displaying or demonstrating today is this one, I2B2. Okay. This is I2B2 2010. This has problem, test, and treatment. So what we are going to focus on is looking for these problems, right? Because these problems are nothing but side effects in the review. And another one that we're going to show you is this BC5 CDR, which is chemical and disease. So from this BC5 CDR named entity recognizer, we're going to pick up disease. Okay. These data sets, right? These are clinical data sets which a lot of doctors have put in effort to create, and they're very large in size. So again, it's not possible for us to directly train on this. So we're going to take a look at how Stanza does it. Okay. First, let's see how to use it. Then we'll go to the documentation. All right. Okay. So I have this Stanza library over here. It's very simple to install it. Just pip install Stanza and it gets done. From this Stanza, I'm going to download two things. Okay. I'm going to download NER for I2B2 and I'm going to download NER for BC5 CDR. Okay. These two data sets, I'm going to download it from. This takes a fair amount of time. Okay. Once it's done, we have both of these available to us. Okay. So I'm now going to create two different Stanza pipelines. Okay. The first pipeline is NLP1. I'm going to use the package mimic, and the processor I'm going to use is this NER I2B2 processor. Okay. So this is basically telling Stanza that whatever model LSTM by LSTM model you have learned for I2B2, pick that up and give me outputs using that. Okay. That is what NLP1 will do. NLP2 is for BC5 CDR. Okay. So this takes, again, it takes a little bit of time to run and all that. It downloads the model, all that pre-processing is done. Once it's ready, we can simply pass a string through this NLP1 object, and uh, it will give us the different things that it detected, right? If you remember, I2B2 had treatment and problem, just these two, right? So, for example, in this sentence, we have, this is my first time using any form of birth control. Uh, I'm glad I went with the patch. I have been on it for 8 months. At first, it decreased my libido, but that subsided. The only downside is that it made my periods longer, 5 to 6 days to be exact. I used it. I used to only have periods for 3 to 4 days max. Also made cramps intense for the first 2 days. So essentially, we have a bunch of problems and a bunch of solutions in this, right? So let us see what I2B2 picked up over here. I2B2 picked up birth control as a treatment. Okay, that makes sense. It picked up the patch as again a treatment. My cramps became a problem over here. Cramps again became a problem. Birth control again became a treatment. The patch again became treatment. Okay. Do you guys notice that it's able to take noun phrases and not just nouns over here? Do you notice? We have my cramps as well as cramps, right? So it's picking up noun phrases to do NER on. This is where we want to get, guys. We have not studied how to get there, but it's okay. It's okay to know that it's possible, right? Okay. So now through NER, we can see that these things are getting detected, right? Okay. Now we'll apply BC5CDR to the same problem. The same sentence I'm going to take. Let's see what BC5CDR picks up. So it picked up cramps as disease. So two things it picked up. Cramps occurred in two places. It picked both of those up as disease. Okay. So this is what BC5CDR gives us. What we are going to do now in the rest of the notebook is simply call anything that I2B2 sees as a disease. I will call that a side effect. Anything that BC5CDR picks up as disease, right? What is the label this gives? So this gives it as problem, this gives it as disease. So whatever is a problem for this guy, I'm going to call it a side effect. Whatever is a disease for this guy, I'm going to call it a side effect. That is what this notebook does for the rest of it. Once we have this, we can see that for each drug name now, we have different side effects, right? So we have orthoevra, which has a side effect of increasing the severity of cramps during period. So we picked this up from that sentence we saw. And same way, we'll pick up different problems for different drug names, right? So in some sense, we have achieved our target. It's just that we didn't train a network from scratch to do that. That's all. Okay. We still are able to achieve our goal of named entity recognition from reviews. And this is how we did it. What we're now going to see quickly is I want to show you how Stanford does this, right? And I want to also take you through this GitHub file. So if at any point you have a very powerful machine to run this, right? I just want to show you what to run. Okay, so this is stanza by this is the demo page. Like I can put a sentence here and it will show me what it gives. I want to just show you stanza library. Yeah. So I just wanted to take you through this biomedical models. I wanted to take you through this description paper. I wanted to show you the results, right, of the training. So yeah. By the way, these are the different models which are available. All of this is documented here in this. Okay. Download and usage is over here. But what we are going to try and focus on is this paper. Let's go to the PDF version. Okay. So just wanted to take you through this section 3. Yeah, actually 1 minute. I have read the earlier version. I'll just go through that. This is a biomed paper. I'll go through the archive paper actually. This is more written for engineering folks. So like one thing is biologists have their own paper formats and engineers have their own paper formats. I find it easier to read it in this format. So yeah. This is the one I had read. I just want to take you to this part. Yeah, this section. Stanza's named entity recognition component is adopted from the contextualized string representation based sequence tagger by this fellow. So these guys in 2018 designed this bidirectional LSTM plus CRF model. Okay. For each domain, we train a forward and backward LSTM character level model to supplement the word representation in each sentence. At tagging time, we concatenate the representations of these char elements at each word position with a word embedding and feed the result into a standard one layer bi LSTM sequence tagger with a CRF. Okay. So everything that you have read here, right? This is essentially that character level predictor, those character level features that I was talking about, right? This is what this is describing. This part, right? This sentence in this paper is basically describing how it is building the input features to this BiLSTM, and the BiLSTM plus CRF based decoder is what we just learned how to implement. So I just want you guys to be confident that you have learned everything that you need to implement something like this. We have just not trained it yet. I also want to take you through what are the resources, computational resources these guys used to show you that this is not possible for us. Just 1 minute, quickly go there. Couple of things I just wanted to point out. Performance, speed, system usage and examples, right? Yeah. No, okay, no, I think that was on their GitHub page. Just 1 minute. The GitHub, Stanza GitHub. Right? So just wanted to show you computations, installation from source, running Stanza. Yeah, training documentation. Yes, this one. So what's nice, guys, is because you have seen this code, right? You can kind of follow this training documentation to see how to run this code. Okay. So if at any point you want to train something with your own thing, you can simply download this GitHub. You can go through this documentation which tells you how they trained it, and you can get this task done, right? So just wanted to point these places out so that if you guys have to implement it in your jobs, this thing. Yeah. Yes, Ajay, you can. You can basically use this. So Stanza's code is written in PyTorch actually. This is written in PyTorch. Let me just check that once. Right? Yeah, this is Torch. See, you can use this code as it is to load whatever data you want and do it. You have to follow this documentation, like I said, this training guide. So the training guide will tell you all the nitty-gritty details if you want to adapt it. Okay. So yeah. Anyway, this kind of concludes our named entity recognition discussion. If you guys have any doubts regarding this, now is the time to discuss this, guys. Right? My request is, if you guys are serious about this method, go through this paper, right? Go through this CRF thing, go through this Stanza's paper. They will have a lot of details for you to replicate the results. That's the nice thing about scientists. They give all the details required for application. Okay. So I'm going to pause here. This is a good time to take a quick 5-minute break. After the break, we'll come back and we'll discuss attention in detail. Okay. Quick check. Is this okay with everyone? If it's okay with you, please hit yes. If not, you can say no. If you say no, I'll say no break. That's all. Okay. Cool. So one last thing. Yeah. Sure. I'll do that. So this is the Stanza paper. This is the Stanza paper. This is this thing on CRF. CRF explained in detail is here. Okay, cool. So follow these links for these two resources. And yeah, okay. Just a general doubt, what level of depth of all of these is asked in interviews for deep learning engineers? So Deepit, I have spoken to a few people who have been selected as deep learning engineers. Generally, they only ask previous experiences of training networks. They will ask you a few questions, common questions like, how do you, like what's the purpose of a skip connection? Those kinds of general things they ask. Uh, they will ask you to do a take-home assignment usually. Okay, so there are 2 or 3 startups where Scalar students have applied, where the task given to them was a take-home assignment. So the depth will get tested in the take-home assignment, not in the interview itself. Okay, so if you want a deep learning role, for the interview, whatever we're teaching you at Scalar is good enough to handle the oral interview. The depth will be tested when by implementation, and how good you are with Keras, right? That is what will decide your selection. So yeah, that is my experience with it. Okay. Anyway, let's take our break, guys. I'll quickly just leave one thing on the screen. Just want to leave one thing on the screen, which is the results, right? So just wanted to show you that Stanza is the state of the art. It is comparable to BERT also. Huh. So you have BioBERT, right? Yeah, this is BioBERT. Stanza actually does quite well on a lot of data sets. So I just wanted to show you this. I kept saying, right, that this is a state of the art, even though BERT has come. This is the proof of that. So bidirectional LSTMs plus CRFs are pretty powerful. Don't underestimate them. So that's all. Yeah. Oh, I see, Ajay. Cool. Hopefully this should help you now. Hopefully this should help you now. Solve that problem. Yeah. Cool. Awesome. I'll see you guys in 5 minutes. Once we come back, let's discuss attention properly. Attention will take us to the next level. All this BioBert results you see here, no? That will be because of attention, okay? So let's come back and discuss that. And we're back. One person is back. Awesome. Okay, quite a few people are back. Awesome. Sorry, I just grabbed a quick bite. I'll just finish chewing. Sorry about that. Okay, so now let's begin a discussion on the concept of attention. Okay, all right. So, to understand attention properly, right, it's kind of important to understand different types of memory. Okay, so let me ask it. Let me ask you this way. We have studied a lot of data structures in Python, right? You've studied lists, you've studied sets, and we have studied dictionaries. Out of the three of these, which data structure do you think best describes your brain? Dictionary, right? Yes, dictionary. Why dictionary? Because in general, human memory is relational. What do I mean by relational? We have a lot of memories, but those memories come into the forefront only when something happens to remind us of that, right? So even in 10th standard and all that, whenever we used to learn things, whenever we used to learn concepts, it would the best strategy would be to build a story around it so that the story is stored in your relational memory and then retrieval happens, right? Yeah. Ajay says doubly linked list. Yeah, you could use a doubly linked list to implement a dictionary, but broadly speaking, right, human memory is relational. You have to first give something and then you will get something back, right? So if you so this happens a lot, even with a lot of good engineers and good researchers that I know, right? You ask them to give a presentation, they will be blank. But you ask them to do a task, they will do it like that. Okay. Why is this phenomenon happening? This phenomenon is happening because most of the concepts that are stored in our memory requires some sort of context to retrieve that, right? And that forms the motivation for attention. Okay. The main motivation for attention is the following. Let us take the methods that we've seen so far. Okay. We've seen RNNs, we've seen LSTMs, we've seen GRUs, etc. Right? In all of these methods, in all of these neural network architectures, guys, did we not see the hidden state or the context state? Were these not simple lists? These were vectors, right? These are basically vectors. Vector is nothing but a list, right? There's no relational stuff happening there. Do you agree or disagree? Agree or disagree? Agree, right? There's no relational stuff happening here. All the retrieval that is happening from these RNN, LSTM, GRUs, right? The memory state is essentially a vector, okay? And that's therein lies the problem. So to understand this idea a little bit better, let us go to the task that we have for today, okay? So the business case that we're going to try and solve today is aspect-based sentiment analysis. Sentiment analysis is very straightforward, right? We all know what sentiment analysis is. Sentiment analysis is all about um, taking a certain body of text and trying to understand if the human who has written this text was happy or sad, something like that. That is sentiment analysis. Aspect-based sentiment analysis is slightly different. Okay, so let's read the problem statement. You're a data scientist in a travel agency. Your company is trying to figure out the sentiment of people about the hotels and restaurants listed on the website on the basis of entities present in the review, right? How do we get entities present in the review? Have we done something so far which allows us to get different entities? NER, right? We know how to extract entities from these sentences. So let us say we take these reviews, we apply some sort of NER on it, and we get to know different names of different hotels, different restaurants, different items that they serve. We can do some sort of NER on them and we can get aspects. Okay, so whenever I'm talking about the word aspect from now on, think of it as an NER tag. Okay, cool. Your company is trying to figure out the sentiment of people about the hotel and restaurant on the basis of entities present in the review itself, so that they could rank the hotel and restaurant accordingly on the landing page. Okay, very common problem. There are many startups which are building aggregators and recommenders. So this is a very common problem right now. They want you to train an ML model to solve this. Okay, so let's understand now what kind of task is this sentiment analysis. Okay, so first of all, there are two things now. I have a review text and I have an entity text. I want to do sentiment analysis on the basis of this entity. Okay, let's understand this slightly better. Let's take this as an example. Ambience was nice, but service was not so great, right? So ambience can be one of those things in our NER tagger, right? Ambience word is something which tells you about how the decoration of the hotel is, right? So here, if I give the tag as ambience, then this is a positive review. In the same sentence, if I give service as a tag, this is a negative review, right? So this is what is meant by aspect-based sentiment analysis. I'm not only going to give you the sentence, I'm going to give you some query words, okay? I'm going to give you some query words on the basis of which you have to tell me the sentiment, okay? So in this sentence, the positive thing is the ambience, the negative thing is service. Okay, everyone with me so far? Have you understood our task? Okay, cool. So this is the task that we're going to solve, aspect-based sentiment analysis. This is a very good example for understanding attention, because the first few modules of attention were designed with something like this in mind, okay? The intuition. So the first model of attention was by this Yoshua Bengio's lab. Let me just open that paper. Is this the paper? No, this is not. I have it on my desktop. Just one moment, guys. I'll just show you the first attention paper. It was actually for a different task. It was for a translator. It was for a Chinese to English translator kind of thing. But the basic idea of attention was introduced in this paper. Yeah. Neural machine translation by jointly learning to align and translate. Okay. So the word attention was not used in this paper, but the computation they used was very similar. Okay. So if you want to trace back the first paper, this is the paper. It came out in 2015, I believe. No, 16. Came out in 2016. So now let us try and understand what is happening over here. Okay. I want you guys to notice a few things here. Do you realize that there is some sort of relational thing happening here? If I'm giving you ambience and you're giving me positive, right? So if you had to think of this in terms of a dictionary, can I say ambience is the key and the value is this positive? Can I say this first of all? Yes or no? So this is the relational part of it, right? Different words here will have different sentiments. The word on the basis of which I want a sentiment is the key. The sentiment itself is a value. Okay. This is kind of important to remember. Okay. So first of all, how do we do this problem? If we did not know about attention, we would directly go for LSTM, right? Because that is just the concept we learned. We saw LSTM gives kind of state of the art. It's not as good as BERT, but it's kind of state of the art. So let's use LSTM. Very easy way to tackle this problem. But again, there is an inherent problem in this LSTM, right? When in all our discussions of LSTM, was there a way for me to give some key and expect a value back in LSTM? Is there any way for me to do this? Not really, right? There are some creative fixes to this. Can anybody think of a creative fix? I just want to see if you guys, if anyone can think about this. Like, there is one very creative fix to solve this problem within an LSTM. Something to do with the first hidden state. Can I do something with that? Can I pass the query word itself as the first hidden state? What do you guys think? What do you think? Will that work? So before it starts reading the sentence, it knows what word it has to focus on. Don't you think we could get that to work? Yes or no? We could, right? Okay. So people have tried this. They have gotten decent results, but attention is better. So let's learn attention. Okay. So now the main focus that we're going to do now is we're going to use something which is known as attention to solve this problem. Okay. So guys, let me give you a fair warning. The concept of attention is a bit very long and lengthy to understand. So what I'm going to do in this class, at least in today's class, my aim is going to be to run you through a fixed method of attention. Okay. I'm going to run you through a fixed method of attention. What do I mean by this? Whatever I'm going to discuss with you today is not attention as we use it inside a neural network. Whatever I'm going to discuss with you today is the basic framework for the equations of attention. Okay. So I need a little bit of cooperation from your side. For today, let us forget about neural networks. Let us just understand basically what is the math of attention. Okay. I promise you, if we understand this today well, next class will be very well prepared to understand how to then take this and fit it into a neural network. So only request from you guys today is if you have questions about how will we put this in a neural network, kindly hold off on that. Okay, kindly hold off on those discussions. Okay, so now let us see. Cool. Let's kind of take this example again. So this is an example of a Yelp review. In this Yelp review, we have this delicious, right? So if our attention is on the word delicious and I ask you what is delicious, what would your answer be? Pork belly. Okay, awesome. One person is awake. If my attention was on the word amazing, what would the item be that I would be talking about? Scallops, right? Okay. So I have amazing scallops. I have delicious pork belly. Okay. So this is what we have. So perfect. What we're now going to try and do is how do we encode our data in a way that if I go for delicious, I will get the associated word with it, right? This is what my objective is. So this is what I have to do here. So now let us try and understand how these attention mechanisms are encoded. First of all, why attention mechanisms? Because they're applicable in most of these things. But yeah, dependency trees could help. Yes, yes, Sean, you're absolutely correct. I could have extracted this from a dependency tree, but we will see why attention kind of does a better job. And it's more general in a sense. It's kind of more general. Let's see why. Okay. Okay. So as we had discussed back in computer vision, attention is new to computer vision. It is still not the best state of the art. That paper which will push push it to state of the art has not yet come, right? Most attention mechanisms are in computer vision at least are not that great, but they're good. So, but they're phenomenally good for NLP. Attention is phenomenally good for NLP. We have seen ChatGPT, we have seen all those things. So we're going to see it within NLP and cross-modal tasks actually. Attention is pretty good for cross-modal also. So yeah, cool. Okay. And Sean, I totally agree. Naive approach is perfect. Yes. Dependency trees, yes. Yeah, that's a good naive approach to do that. Yes. Attention mechanisms have to overcome RNNs. Yeah. Okay. So why attention plus LSTM? We'll discuss that later. I'll explain this once we have understood this properly. Okay. So, okay. So guys, this is where we're going to start discussing the mechanism of attention. Okay. So first, let us see what all components are there. I have my key, query, value, energy function, alignment distribution, final representation. How many of you think this is totally ununderstandable right now? Is this is not understandable? Okay, fine. So what we're going to do now is to understand each of these things and what their purpose is, right? We're going to take one sentence as an example and we're going to apply all these steps on that sentence. And we're not going to talk about how to learn stuff here. We're only going to see how to do this naively first. Okay. So let's get to the math of this. Cool. So all of this is there. Let's ignore this for now. All of these are also there. Let's ignore it for now. All this complicated stuff is there. For now, let us just understand broadly what are the steps that are required, right? So let's focus for a while on this diagram here. Once we understand this diagram, okay, once we understand this diagram to some extent, we can take up the example and we can go through that. Okay, cool. Awesome. So this is what computing attention looks like. So first of all, keep in mind the concept for attention comes from relational memory. Okay, this is a bit like a Google search. You can think of relational memory as Google search. I will first give you a query. You will give me the response to that query, right? So there are three things into play. There is the data that we have. Those are nothing but the keys. There is the query, which is something I'm giving you. And then using the query, you have to match the query to a certain key. And then the value of that key is what you have to give. Okay. So what's the basic difference between just a dictionary and a dictionary based on a query? What's the difference? The difference is one additional computational step. The additional computation I have to do now is I have to somehow take my query, I have to do some computation on it so that it can be matched to a key. So that query to key mapping is where we have to do computation, right? That idea is sort of going to be used here. Okay, so let's see now. So first of all, the first step is always to get key vectors. Okay, so let's talk about this for a second. What is the data that we're dealing with? Are we dealing with text data? So isn't my data essentially going to be a sentence? It's going to be a sentence, right? Okay. So let us say I have a sentence. In fact, let me take the sentence with which I'm going to discuss the example, right? Let's take this sentence. Food is delicious, but price is high. Okay, let's take this sentence. Food is delicious, but price is high. Okay, cool. So let us think of this sentence as a concept that we have to remember. Okay, let's think of it as a concept you have to remember for now. Can you guys tell me, at the lowest level, what I have is these individual words which are coming together to form a sentence, right? Have we learned how to convert these words to vectors? We have, right? Word to vec. We know how to convert these words to vectors. So whenever I'm talking about getting the key vectors, the key vector is going to be made up of things that I'm trying to remember, right? I'm trying to remember this concept. So my key vectors are going to be nothing but representation of my sentence. How am I representing this over here? I'm going to take each word over here. Okay, I'm going to take each word over here. I'm going to get a vector representation for this. Okay, and what I'm going to do is for this entire sentence, I'm going to build a matrix by arranging these in the correct order. Okay, so the first column. So now imagine that getting this key vectors is going to be nothing but getting a set of vectors from this sentence, right? So my first column here is going to be the vector representation for food. My next column is going to be the vector representation for is. The next one is going to be delicious and so on. Okay, cool. Let us say that the word to vec dimension is D. Okay, D is word to vec dimension. And let us say the length of my sentence is n. What will be the dimensions of this? Will it not be d cross n? D cross n? Okay, it is going to be d cross n, right? So whenever I'm saying get key vectors, what I mean is I'm going to take my sentence, I'm going to convert that entire sentence into vector form, and I'm going to keep that as my key vectors. Okay, why? Because this is the sentence on top of which I have to do something, right? I want to get contextual information on this sentence. So whenever I'm applying attention over here, my key vectors are going to be the sentence that I'm getting. Okay, cool. Now comes the question of query vectors. We discussed this, right? How do we get query vectors? Using something we've used before? NER, right? We'll use NER. So we'll use named entity recognition to get words from this. Okay. Let us say NER tells us that one aspect that is of interest to us is food, right? If we're classifying restaurants, I have to be able to tell you how good the food is. So let us say food is picked up as my context. Then how do I build my query vector? Very simple. I'll do the same thing. I will take food, I'll take the word to vec representation of food. Okay. So this can be one example of a query vector. This is nothing but word to vec of food. And let us say I want to also ask how is the cost of this place, right? How is the cost of this place? So another query I can consider is word to vec of cost. Can you guys tell me, does the word cost appear anywhere here in this sentence? No, right? Yeah, cost is not in the sentence. This is why I gave this example. It is okay for cost to not be in this sentence, okay? We are going to now rely on word to vec to tell us that the word cost is closest to the word price over here. Okay, this is a little counterintuitive, but bear with me. We are going to rely on word to vec to capture the relationship between price and cost. And I just wanted to show you that the query vector does not have to be in your corpus as long as it is there in the corpus of word to vec. Okay, this is where we're now slightly moving towards this thing, transfer learning, guys. I don't need my query vector to be in the corpus. Do you not see how good this is? This is, I mean, at least I was excited when I thought of this. So yeah. So we can now start using synonyms to search on our text. Why? Because the word to vec itself is going to be so good that it's going to capture these similarities. Okay, we're going to see how this is done through an example. Okay, cool. Now, once we get this key vector and this query vector, we have to compute an energy score. Okay, guys, energy score is a very new terminology, right? Let's forget this. Instead of energy score, think of this step as finding similarity between keys and queries. Okay, we know how to do this from the first class only, right, guys? If we are given two vectors, we can find the similarity between those two vectors. What all methods do we know? What all methods do we know to calculate similarity? Cosine, dot product, similarity score, all of these are perfectly valid. Okay. So when I'm saying compute the energy score, what I'm asking you to do is simply find the similarity between this query vector and every column of this key vector. That's all I'm asking you to do. Okay. Now let us, for example, assume that I'm going to use the dot product for this. How do I get the dot product between this key matrix and this query vector? Matrix multiplication? Can I apply simple matrix multiplication here? Will the matrix multiplication give me dot products? It will, right? Are we confident of this? Quick check, guys. If I take matrix, I take a vector and I do the multiplication, I'll get the dot products, right? With the columns. Or will I get it with the rows? What will I get it with? Key.t and dot query. Perfect, perfect. I get the dot, guys, when I'm taking the dot product, I'm taking the dot product of the row with this, right? So what I have to do is I have to transpose this. I want to take the dot product of this with the columns. So I have to do a transpose operation here and then do it. That's all. Anyway, if guys, if you did not follow the last 2 minutes, it's okay. It's not important. We will see it clearly in the example. I was just testing your math thing. That's okay. Ignore that. Let's come back to this. I now have a vector representation for my keys. I have a vector representation for my queries. I have calculated the similarity between them. Okay, I've calculated the similarity between them. Now things start getting a little complicated. Okay, so follow along. This energy score that I'm going to get out of this, is it a probability distribution? Is it? Is it guaranteed that it will be a probability distribution? No, right? Because dot product can take any value. It can take any negative value. It can take any positive value, right? If I take any two vectors, take the dot product, it can take any positive value, any negative value. So if it's taking negative values, can it be probability? No, right? No, it cannot be. So say confidently, no, it cannot be a probability distribution. The energy scores output cannot be a probability distribution, but to do attention, I will have to forcefully convert this energy score into a probability distribution. Okay, convert this to probs. Which function? Ajay, come on, we know how to do this. Ah, Indradeep knows it. Softmax. I give you a vector, I ask you to convert it to probabilities. You can simply apply softmax. So this is one way to do it. Of course, there are 100 techniques. Just like we could have had 100 ways of calculating similarity, we can have 100 ways of calculating the probabilities associated with it. But today's example, we're going to see softmax. Okay, we're going to see softmax in today's example. Okay, so I will take this energy scores. It's going to be a vector. Matrix times vector is a vector. I'm going to apply softmax on it. I'm going to convert these to probability values. Okay, now comes the fun part. Whatever I'm getting as the output at step 4, right? It's going to be a probability vector. Okay, guys, it's going to be a probability vector. It's going to give me the probability of these words with respect to those queries. If you think about it, it is going to give me probability that the query term is related to this vector term. Agree or disagree? Do you guys see it? Whatever I'm getting at the end of step 4 is going to be like a probability distribution on which word in the key sentence is close to the query word. I'm going to wait till you see this. Okay, I'm going to pause till you see this. This is kind of important. Again, if you're not able to see it, let's see it in the concrete example. But I want at least one person to agree that this is going to be probability that this word is similar to this query. Can one person agree with me at least? Okay, I'll re-explain. What is energy score? Energy score is the similarity between my key and my query, right? Energy score is nothing but similarity. If I convert these similarity scores into probability distribution, won't I get probability of how similar is my query to my key vector? Yeah, perfect, cool, awesome. So at least one person agrees. 3 people agree. Perfect. Okay. So now I have a probability distribution on which of these words are important with respect to what I'm paying attention to. If I'm paying attention to food, I will get food as the word. If I'm paying attention to cost, I will get price as my word, right? Okay. Question is, how do I actually get the value that I'm after, right? I'm asking you for the sentiment associated with this word. I don't want the word itself. I want the sentiment associated with this word. This is where I have to take this probability distribution. I have to weight my value vectors with it. Okay, so my value vectors, I'll explain how these are coming a little later. For now, just imagine that we have these vectors which are going to capture what the sentiment is. Okay, how to get them, we'll discuss. I'm now going to use this probability distribution to weight my values. Okay, I'm going to simply multiply this value vector with this probabilities, and I'm going to compute something which is known as a context vector. And finally, it is this context vector which will give me the sentiment. Okay, it's the context vector which is going to give me the sentiment. So this is how attention is implemented. Okay, these are broadly speaking the steps: key vectors, query vectors, energy score, attention score, value vectors, context vectors. Let's actually do this through an example that will solidify the idea. Okay, so follow along with me. We have this sentence now. Food is okay. Guys, before I move on, I'll quickly recollect. Okay, sure. Anil and Sean, I'll quickly recollect for you guys. Key vector, okay, is a vector that I form for my sentence. Okay, I take a sentence, I form a key vector for it. How? I will apply word to vec on each word and I will stack them up in order in the matrix. Okay, the order is important here. So don't forget about the order in which these vectors come. Query vectors are the words with respect to which I want to get some information. So cost is one example, food is another example. Remember, query vectors need not be in your corpus. Energy score is nothing but the similarity between these two. Attention weights is the probability version of the energy score. Why? Because I'll tell you. This is for a math reason. Step 4 is for a math reason. Okay, we'll see that. Then I'm going to have something which is known as value vectors. Again, we're going to come to this later. Why? Because this value vectors definition changes from application to application. Okay, it changes from application to application. So we will discuss this when we see the example. Context vector is finally the vector which is encoding your sentiment. Okay, why this is encoding my sentiment, we will see. Right? Okay. How are my query vectors calculated? I will take the query word, I will convert it to word to vec. Simple. Got it? I'll take my word, convert it to word to vec. Yeah. Anil, is this okay? Can I proceed with the example now? Okay, perfect. Let's move on. So my sentence is food is delicious, but price is high. Okay. Now, here is the thing, guys. To do word to vec, right? Instead of word to vec, you can use this amazing thing called Glove. Okay. So Glove is basically word to vec plus some additional things. Okay. So Glove is this nice library which has been written by these people. What these guys did was they took a word to vec kind of architecture and they changed the objective function of that. So let's go through this. Glove is an unsupervised learning algorithm for obtaining vector representations for words. Training is performed on aggregated global word-to-word co-occurrence statistics from a corpus. This is a very fancy way of saying they will get the word-to-vec kind of matrix. They will basically see which words, they'll get the bigram matrix. You remember when we discussed bigrams? I have the words on one column, the other words on the other column, and the co-occurrences frequency I'm going to put in the matrix entries, right? So what these guys are doing is they're going to take that matrix, they're going to apply some sort of matrix factorization technique there along with a neural network architecture. And finally, what they get is this Glove. Okay. So Glove is like word to vec, but better. Okay. I'll just attach this over here for you guys. Like I'll leave it in the pinned messages if you want to check this out. Why is this important is for the following reason. Okay, guys. What is nice about Glove is that it has something which is known as linear substructures. Okay, linear substructures. Let me explain this to you slightly. Okay. Let us say I take the word king. Okay. And I want to do some sort of vector operation to reach queen. Can I not subtract the vector man from this king and add the difference between woman and man to this king to get queen? Okay, I'll repeat this. This may be a bit complicated. A king is there. Okay, a king is a man. If I subtract man from king and I add woman, right? If I subtract man from king and I add woman, shouldn't I get queen conceptually speaking? I should get queen, right? Conceptually speaking, I take the vector for king, I subtract man's vector from it, and I add queen vector to it. That is exactly what is happening here, guys. Think about it. Man vector is here, woman vector is here. Woman minus man is nothing but a y direction change. Okay? Woman minus man is nothing but a y direction change. If you notice, king to queen is also y direction change. So this is what I mean by linear substructures. The meaning of linear substructures is we can take these words, we can do some arithmetic on these words embeddings, and they will give us sensible things. Isn't this cool? Like if I wanted to explain to a child what is a queen, it's nothing but a king minus man plus woman, right? It's a very simple idea. I can actually do this with math if I use Glove embeddings. Okay. Yeah. Indradeep, yes, we saw a similar diagram in word to vec, but Glove works better than word to vec. Word to vec is not always guaranteed to give you good results. Glove is like a better version of it. So in general, I've seen only people use Glove for attention-based mechanisms. That is why I'm putting this forward. So yeah, okay. So that is what. So now what we're going to do is we're going to take this Glove library. So let me just show you where I've imported it. So yeah, okay, there is no such thing as a Glove library. A Glove is present in this gensim. Okay, so from gensim.downloader, so we have this gensim.downloader, right? So from this I'm going to import Glove, I think. Glove vectors is gensim.downloader.load Glove Twitter 25. So basically they took the Twitter 25 dataset, they trained Glove vectors on it, and that is what we're getting here. Okay, cool. Now let's see this. I have taken my sentence, okay, food is delicious but price is high. I'm going to convert this sentence into Glove vectors, okay? But for the sake of this example, right, I don't want to use a 200 dimensional vector, okay? It's too tedious to track. So for the sake of this example, I'm going to apply PCA on it and I'm going to reduce the dimension to 5, okay? Is this fair? From what we understand about dimensionality reduction, is it okay if I do this? Will this work? What do you think? So it'll work decently, right? For the sake of an example, it will work. So let's do this. I'm taking this huge Glove vector. I'm converting it to a 5-dimensional vector because I want to work with a smaller dimension. And we're going to understand everything with respect to this example. Okay, so let's do this. Now, my key is nothing but PCA.fit transform on key. Okay, key was initially the Glove vectors. Let us print, in fact. No, it's not connected. Okay. I can't mess around with this. Okay. Yeah. So it's basically converting this to a 5-dimensional vector, and we have this key vector matrix over here. Okay. On the rows of this, I have the words, right? On the columns, I have the dimensionality of my embedding vector, right? So do you agree that this is a D cross N matrix? Is this a D cross N matrix? It is, right? So we now have a D cross N matrix here. Now let's get the query. How was I getting query? I will take a single word. So remember, I told you query examples was food and cost. I'm now going to take the word cost. I'm going to apply Glove on it. I'm again going to do PCA so that I can get the 5-dimensional version of this cost word. Okay. And I'm going to plot this. So now my query vector is just this word cost. Okay. It's 5-dimensional. This is what the vector looks like. Is query always a single word? No, Indradeep. I could have totally done cost comma food here. I could have totally done this. In fact, I want you to try this. If all the code that we have written, right, will work for this example also, where I have taken food comma cost. So yeah, but for the sake of simplicity, see, I have to explain this, no? So to make it simple to explain, I'll use this example. Okay. So this is how I get my cost. Now we're going to compute the energy function. Like I said, energy function is nothing but the similarity between my query words and my keywords. So all we're going to do here is compute energy score. We're going to simply multiply this with this. Am I allowed to do this? This is going to be D cross N. This is going to be D cross 1. No, I'm not allowed to do this. Now I have to do a transpose. So I'm going to do transpose of this and I'm going to apply this, right? Just 1 minute, guys. I think I'm confused here. When I'm doing this key df, am I doing a I'm doing a transpose here. That's why. Okay. My bad. I'll just revise this. This has to be a n cross d matrix. My bad. Okay, actually it's okay if I keep it here. It's only a transpose difference. So yeah, it won't cause a problem. Let's kind of follow through with this example. Just want you to remember right now, my key matrix is, so actually let's create a new thing. Okay, so in the example, key is a n cross d matrix, where n is the length of sentence, d is length of embedding. Okay, this is what I have. I just want to make these notes so that I can keep track of it. Then my query vector is a d cross 1 vector, right? So second thing is query d cross 1 vector. So am I allowed to do a matrix multiplication between key and query? I'm allowed to do this, right? N cross D, D cross 1. So this is going to be an N cross 1 matrix, the output. Okay. So energy function now, or the energy score, is nothing but the matrix multiplication between my uh, key matrix and my query vector, right? My query is my vect over here. My key is my mat over here. So my key into my query will give me this energy score. Okay, cool. Now comes the point of converting this to a probability distribution. See this implementation of softmax. Is this correct, by the way? X is np dot array of x. E to the power x is np to the power np exp of this. And what I'm returning is this divided by the sum of this. Right? So this is correct implementation of softmax. My attention weights are nothing but the softmax of this energy score. That's it. Very simple. The job of this attention weights is to convert this to a probability distribution. So I'll just convert this to a PD data frame and plot it. So now my attention weights look like this. Okay. My attention weights with respect to query vector looks like this. High is price, but delicious is food. Oh, sorry, I read it in the opposite way. Food is delicious, but price is high. What is nice here is our query vector was cost. Remember, cost was not in our vocabulary. Price is 0.99 here. So our attention now is fully on this word price, right? The topmost entry over here is this word price. The second topmost entry is food. No, it's not food actually. It is high, in fact. That's interesting, right? The second topmost entry over here is high. So we have price and high over here. Okay. So this is where we are, right? Okay. Cool. So now let us now take this thing, key query. We have attention weights now. Energy score is now going to be this n cross 1, right? Yeah, n cross 1. Attention weights is also going to be n cross 1. And now let us see the other parts. Okay, cool. Okay, guys. So, guys, in this example, right, in aspect-based sentiment analysis, do I not have to detect something within the sentence itself? I want to understand something about the price, but the destination of this prices concept is also the same sentence, right? I want to now understand what is the price, sentiment associated with price in the same sentence. So that is why in this example, what we're doing is the value we're going to set equal to the key. Okay. In general, when we want to take a sentence but make an inference about some other body of text, then I have to set my value to that other body of text of interest. Okay. That is how we generally set the value. The value is the place where I want to do some understanding from. Okay. The value is usually the place where I want to gain some insights from. Right now, we're setting the value to be exactly equal to the matrix of key. Okay. So if you notice, my value is going to be 7 cross 5 and my key is also 7 cross 5, right? Okay. So what you have to understand about the value here is value is the place where you want to do analysis. For our example, the analysis place is the same sentence. So we're going to put value equal to key. Very simple. Now let's come to the context vector. Context vector is going to be nothing but the same value vector. Okay. So remember, we have now paid attention to something and we have some attention scores. We are now going to apply those attention scores to our value matrix. Okay. To our value matrix. How are we going to do that? Don't you think if I simply, okay, so 1 minute, I'll have to draw this to explain this properly. Okay. So let me first write down the sentence. Food is good, but price is high. Okay. So let us say over here, I have the glove embedding. This is the glove embedding for this. This is the glove embedding for this. Glove for this. Glove for this. Glove for this. Glove for this. And for this. Okay. I now also have an attention weight for each word, right? Remember, my attention weights are n cross 1. So if you notice, there is an attention weight, there is an attention probability associated with each of my words. Okay, each of my words here. How do I apply this attention to my matrix here? Can I not just take the attention weight for food? So what is the attention weight for food? It's 0.0018. For is what? Something 4.1. Okay. Price was 0.99 and sorry, price is 0.99 and high is 0.049. Okay. Now what I'm going to do is I'm going to take the value matrix. Remember guys, this is the value matrix, not the key matrix. This is the value matrix. Value matrix again is nothing but a stacking of these glove embeddings for each of these words. To apply attention here, all I have to do is multiply this weight with this column. Okay. This is what I'm doing in step number 6. I'm simply multiplying this probability value that I have seen with this weight matrix of that glove embedding. Do you guys realize in that space, in that diagram of glove embeddings, what is happening here? Do you guys see that I'm adjusting the importance of these things, of these words? Is that part clear to everyone? I'm essentially taking the same vector, I'm adjusting the importance. The length of that vector is the importance there, right? So I'm essentially adjusting the importance of that through this computation. So this apply attention score is going to be nothing but a element wise multiplication. Okay, it's an element wise multiplication across the column. Okay, I'm going to take this weight, multiply it for all entries in this embedding. That is what's happening here. So annotations of colon comma I. So colon means what? For all the row entries, and for the ith column entry, I'm going to take attention weight I and I'm going to multiply both of them and I'm going to store it in something known as the attention weight. So applied attention is this thing. Okay, it's going to be a matrix. So once I have applied my attention, this is what my vectors will look like. Okay, this is what applied attention looks like for the query, not food, right? The query here is cost, not food. Yeah, query cost actually. Should have seen that before. Okay, anyway. So this is how I'm going to get this attention, this thing. And finally, if I want to get the entire context of this whole thing, right? So right now I have a embedding per word, but now if I want to convert this to a context vector, I simply have to flatten it. But which dimension will I flatten it across? Which dimension will I flatten it across? Should I flatten it across the words dimension or the embedding dimension? Which one makes more sense? Where should my context vector lie? It should lie in the same space as my glove embeddings, right? So the length of my vector should be the same as my glove vectors. So I should now add everything up along the word dimension, not the embedding dimension. Okay. Sorry, Azhar, I think you are answering the question. The dimension. Yes, you're right. The dimension has to be the embedding dimension. So we are now going to simply sum all the values across this, and we're going to get a context vector food. Not food again, this is cost. Okay. Cool. So this is how attention is computed. I want to just point out to 3 or 4 main takeaways from this before I end today's lecture. Okay. Just few takeaways before I end the lecture, guys. Please bear with me. Stay with me for 5 more minutes. Whatever you saw today, right? Attention mechanism. This is a way for us to get importance associated with embeddings weighted in a certain way, right? So the basic intuition here is I want to have fine-grained control on what my context state is. I want a key value pair kind of representation where my key vectors is basically some textbook that I have studied. My query vectors is like the question paper question, and my attention weight will allow me to write my answer. Okay. So I want you guys to really, really solidify the intuition over here. Okay. Think of this key vector as the textbook you're studying. Okay. Imagine that in your brain has created these vectors for all the concepts in this textbook. Your query vector is the question that is asked to you in an exam, and the context vector that you're constructing over here is the answer. The final answer that you're giving is the context vector. How are you getting this context vector? You're first taking the similarity between the question and all the concepts you've learned. You're getting one probability distribution out of that. You're getting one template answer, and you're adjusting this template answer based on your understanding, right? So that is how all of this fits in together. And it's very important to keep these computational things in mind, because this computation is what we're going to take and we're going to build a neural network around this now. Okay. And it turns out if we do this, we get ChatGPT. Imagine, it's that powerful. The idea that we have discussed today is that powerful. Okay. Don't underestimate this. Please try and remember these steps. In the next class, I will do a quick recap of this, and we will see in detail how to now build a neural network around it. So I just want to show you these diagrams. There are different types of attention mechanisms. Once we get them, we can construct these neural network layers out of it and do all our tasks. Okay. Yeah. Cool. So Ajay is requesting for a recap for value vector. I'll quickly do that. So in the example that I'm giving you, key vector is the textbook, query vector is the question in the question paper, value vector is like a template answer. Okay, think of the value vector as a template answer. Your context vector is going to adjust this now. So let me do it this way. For the example of aspect-based sentiment analysis, my query vector and my value vector are the same. No, why? Because I want to understand the sentiment of that word in that same text. If I now, let us now imagine that, yes, key and value here is the same. No, not key, sorry, key and value here is the same. Yes, not query and value. That is self-attention. I'm sorry. So 1 minute. Let me rephrase this. Imagine your value vector to be the same textbook and your context vector to be your final answer. So you're basically taking the attention, you're applying it to your textbook, and you're giving an answer in your own words, right? Based on your understanding. So yeah, that is how I would modify this example. Textbook, question paper question, textbook again, and final answer. Okay, let me write it in the diagram. Intuition, just 1 minute. I'll just write it in the diagram itself. अरे नहीं यार. So let's take this analogy. Okay, so this is the analogy. I have textbooks, I have my query vector. This is like you're recalling the answer. You're giving your final answer in the form of a context vector. So this is the thing. Okay. I'll quickly take up the other doubts. Oh, guys, sorry, by the way, I'll just start the doubt session. Those of you who don't have doubts can leave. I'm actually done with the content. Next class, guys, please revise this one diagram, okay? Just revise this diagram, sincere request, because if I keep repeating it, I'll keep extending classes. So just revise this and come. So thank you. Yeah. Indradeep says, so I'm kind of scaling the same sentence based on the query when I'm multiplying by the value matrix. Yes, yes, Indradeep, you are. So at the end of step 4, you have an attention matrix, right? You have basically encoded what values you should pay attention to, what words you should pay attention to. Then I can apply this attention weight to whatever value vector I want. Why? Because of the dimension of this matrix. Think about it. The attention weights, the dimension of this attention weights is going to be what? N, the length of your sentence, right? So I can now, in principle, apply this to, I can basically take these attention weights, I can encode it in a one hot encoded form, and I can multiply it with anything here, right? So like that. Okay. So like that. Yeah. So I'm basically applying attention there. So I can do it for anything, but in this example, which is context-based, sorry, what's the problem name? I keep aspect-based sentiment analysis. We'll set this. Yeah, that's the idea. Yeah. So key and value is the same. Ajay's question is for the query, cost value vector is price. For the query cost value vector is price. No. For the query cost value vector is the sentence itself, right? Ajay, see what we're trying to do here. We want to ask the question, what is the price like? Where is this information stored? It's stored in the same sentence. So if this answer was stored in a different sentence, no, then I would change my value. But for this example, what I want to do is I want to find the answer to this question in the same sentence itself. That is why I will set the value equal to the key. Clear? Okay. Anil, yeah, Anil, I'm so sorry. If possible, just rewatch this part, the attention part. It's very intuitive and it's very exciting because this, like, people use this a lot, right? So my request is just follow through. If you have any doubts, right, please reach out to me. I'll do my best to answer your questions on Slack. Yeah. Recap is a must. Okay. I'll make sure I recap next class. I'll recap next class. I'll give a short recap, but I will sort of run through it. Okay. I won't go through it for half an hour. I'll probably do it in 10 minutes. That's all. Okay, cool. So let me quickly take the questions which have been asked in the questions tab, and then we can end the class. Oh, from your side. Okay. Nothing much. Don't break your head. No, all you have to do is see. I have skipped most. So I'll give you a suggestion. Look at this. Look at this one, and look at these figures. That's it. That's all you have to revise. Yeah. Ajay's question is: we multiply prob score with the vector itself. We multiply the prob score with the vector itself. No, we multiply it with the key matrix actually. Sean, yes, I am sharing the notebook right away after the class ends. You will have access to this notebook. You can read ahead if you like, but my request is at least read till here. Cool. Okay. Awesome. Now, Ajay, I wanted to answer Ajay's question. Ajay, we multiply this attention weights with the we multiply this with the key matrix. Why? Because we said key equal to value, no? That's all. So we're multiplying it with this. So n cross 1 is being multiplied with n cross d. This is allowed, right? So I will get a d cross 1 now. In case this matrix mismatches, right? You have to pad it. So think about it this way. In case you're using a value from somewhere else, you have to just pad it or reshape this in a proper way. Then you'll be fine. Okay. Yeah. Okay, guys. I'll quickly now take the two questions on the questions tab. First one is Naveen's question. Can you briefly explain how sigmoid focal cross entropy handles imbalanced data? Definitely. First, let's go to the paper. Where's the paper, dude? Yeah, it will be here. Here. RetinaNet paper. So it was actually introduced in this RetinaNet paper. They use this to improve the performance of this. So RetinaNet is a object classification network. Okay. The basic the basic change, right? The basic change in the cross entropy formula is instead of using summation over minus log of P of t, they are now going to do a summation over minus log of P of t multiplied by this 1 minus P of t to the power gamma. Okay. This gamma is something which is now variable. Okay. So for gamma equal to 0, what is this going to be? It's going to be simply 1, right, Naveen? For gamma equal to 1, this is simply going to be 1. Correct? Just checking if Naveen is still there. Naveen is here. Okay. Right? So if I put gamma equal to 0, I will get my usual cross entropy loss. If I put gamma non-zero, then look at what's happening here. If I put gamma non-zero, my loss function will now be artificially lowered for low values. Let me explain this intuition slightly. Okay. I want you to look at this 1 minus pt, right? So if pt is low, 1 minus pt is a high value. Okay. So if 1 minus pt is a high value, if I put gamma which is greater than 1, this whole thing becomes now a low value. It becomes lower, right? If pt is high, this brings down the importance of this. Okay, so now let us understand the relationship between this term and this term. Okay, in fact, let me take it here. Okay, so let's look at this. And first, let's talk about the issue. The issue is a class imbalance. Okay, let us say for T, which is high representation, PT is high, right? So what is the fundamental meaning of the class imbalance problem, Naveen? If I have a class imbalance, any class which has very large number of examples, the probability of that will be exaggerated, right? Do you agree with this statement? So probability of a class is being exaggerated right now. I want to bring down the importance of that. How do I bring down the importance of that? I will take this log probability, I will multiply it by a function which is inversely dependent on this PT, right? It's inversely dependent now. So this 1 minus pt to the power gamma, if you think about it, if pt is high, this value will be lower, right? Agreed? So that's the idea here. I'm going to now apply a weighting function. So think of this as a reweighting of my probability terms. I'm going to take this pt value, I'm going to multiply it with this 1 minus pt to the power gamma. So effectively what happens is anything which has artificially high pt, its importance is brought down. Anything which has a low pt, its importance is bounced up a little bit. So this way, it sort of applies a reweighting to your loss function. So think of this as your old cross entropy with new weights, where the weight is determined by this equation here. Cool? Is this now clear? How focal loss works for imbalance cases? Awesome. So yeah, I'll just mark this as answered. Cool. So now Satish's question: how attention mechanism will work in computer vision? Any example code and corresponding paper? Satish, see, I'll tell you one thing. Okay, I have read this. I have read the computer. I have read the CV version, right? Essentially, the basic funda is the same. Only thing is, instead of key vectors now, this is going to be an image, right? This is going to be, it's not even going to be an image. It's going to be an image embedding, okay? this query vector is now going to be a word, or it could be a word embedding also, it could be a sub image embedding also. So that is the problem with computer vision. Okay, there are so many ways to do it that I can't find one good paper where everything is explained clearly. They make things complicated, and I myself have not come across a paper where it is explained clearly. So let me do one thing. Let me go back. Let me search for a good example where it's easy to understand, and then I will share it with you in the next class. How about that? So I'll just note down one thing for myself. Okay. So I know of one example. Okay. Essentially, you take an image, you take this as the word embedding. The energy score will basically take the. So this is going to be a common embedding between images and words. Okay. So cross-modal embedding here, word embedding here, this is going to compute the similarity between the cross-modal embedding and this. The attention weight is going to be weighted by that. My value now is again going to be an image. So think of the value here as the image. When you multiply these two, it is going to highlight which part of the image corresponds to which part of the word, right? That is how this is usually done. Let's actually search for an example right away. This is a survey. Okay, let's go to the survey. Okay, this looks like an excellent paper for me to go through and come back to you. Uh, cool. So, Satish, I'll look for an example. Okay, I'll do one thing. I have found this paper, which is a survey paper, right? So all I know about computer vision attention is they basically change these things over here to get something. For each of these tasks, it's done a little differently. So I'm a little not sure of which comes where for what task, right? I will look for a paper with code and I will share that link with you next class. I'll just remind myself that I have to do this. Okay. I've written a reminder. I usually go through my own notes like once the class is done. So I'll remember to do this. I'll share it with you in the next class if it's okay. Is that okay? Cool. Thanks. Cool. Does anyone have any questions about the content in today's class? This is kind of getting heavy, right? We're learning the code of the last class and the concept of today's class, which is unrelated. So it's kind of unfortunate. I think I'm putting a lot of people to sleep. So yeah, sorry about that. Uh, I mean, I've tried my best to keep things sensible, but hopefully the break makes up for it, right? Does the break make up for it? Okay, cool. Cool. Let's do one thing. I'll try my best to align these. Okay. This is not good. Like code of last class and concept of today's class is not good. So I'll see what to do to align it. But yeah, let's see. Yeah. Anyway, does anyone have any other doubts? I'd be happy to take the doubts today. Uh, if not, one extra class in between. Okay, sure. No, but the Anil, the problem is this, no, in that extra class also, what will happen is I have only 1 hour of overlap. So I'll have to, what will I do for the rest of the hour? So that's the issue. I'll think about it. I'll think about this problem. I'll see what to do to fix. I'll probably do one thing. I'll extend the class for next week. Next week is anyway Transformers. No, Transformers is nothing but attention only. Yeah. Okay, class for backlog and query resolution. Yeah, short class of 1 hour, and then we can do 1 hour of discussion on other stuff, right? Like so some people ask me some very good questions. I get the answers, but I don't revert back. So I can keep 1 hour for that maybe. So let's try and do that. Let's try and do that. Next class is going to be better, guys, because transformers do nothing but attention. So next class, the concept that we'll learn and the code that we'll see is also same. So I think it will be okay for the next class. The class after that, I will try to do that 1 hour of this plus 1 hour of that. I'll try to do that. And then finally, when we learn bird, we will do it in a fresh class. Let's see if we can do that. Okay, awesome. Thank you so much for your attention to the attention lecture and good night. Good night.